Far-field 3D detection, or in short, Far3Det, is a paper that focuses on far-field aspect of 3D object detection in autonomous driving. We propose a method to curate high-quality annotations from an existing dataset along with some evaluation metrics. Finally, based on our empirical findings, we also propose some multimodal fusion methods. The first question that comes to our mind is why far-field detection is important. Turns out on highways, the typical driving speed is 60 miles per hour, giving rise to a brake distance of 70 meters. So we need to have at least 70 meters of detection for highways. Even in the city, we might encounter an unprotected left turn, giving rise to similar brake distance. In order to study far-field 3D detection, we need a data set with high-quality annotations at high distances. However, on analysis of popular benchmarks such as Waymo, Kitty, and nuScenes, we found that all of them have missing annotations. Therefore, we performed a semi-automated cleanup to sample high-quality data from nuScenes, and we termed it as Far3Det. When we performed an analysis on randomly sampled set from all these datasets, we found out that our Far3Det dataset has much lesser missing annotations. Interestingly, when 3D object detection was introduced, the metrics was simply derived by extending 2D MAP to 3D MAP using 3D bounding box overlap. In a human driving scenario, we need to have precise understanding of nearby objects, but only an approximate idea for the faraway objects. Hence, we propose to have a variable thresholding scheme where the threshold can be a function of distance from the eco-vehicle. Finally, we retrained the SOTA, LiDAR, and RGB models for higher distance range, and we found that RGB methods outperform the lidar-based method by a high margin provided we use the right metrics.
Simple yet effective technique to fuse lidar and image-based detections with respect to distance. We call this technique adaptive NMS, where we scale our IUU threshold linearly with respect to distance. We see promising results from adaptive NMS when we compare it to LiDAR, RGB, and late fusion baselines on far field. Overall, we observe that LiDAR-based methods perform good on near field, poorly on far field, whereas image-based methods perform good on far field. Our fusion method performs good both on near field and far field. We also update our evaluation benchmark by including non-occluded zero lidar point boxes, which are often discarded by other benchmarks to get a boost in performance. We propose a frustum-based heuristic to determine occlusion level. Overall, we discard only those boxes which have no lidar return across the 10 sweeps and are occluded. Using this updated benchmark, we see that our method significantly outperforms the state-of-the-art fusion method at the time.